I come at the world from a very different perspective. Perhaps I'm the odd one out. I'm an evolutionary biologist, an ecologist, and an ecological designer. And where we start in this whole business of intensification of agriculture in an urban setting really needs to begin with, contemplating a meadow or a field or an orchard as we conventionally understand it. And underlying those systems is an ecological infrastructure upon which agriculture totally depends. And there's a lot more information in those soils and structures and hydrologic cycles than we can really imagine. But the important thing is that they're all borrowing from a over 3 billion year legacy of the evolution of life on Earth, of the evolution of the 6 kingdoms of life and how they've interacted and interlocked. And my hypothesis today really will be, how can we, because we really are helping design the future, integrate nature's operating instructions, nature's genius, into our intensive urban systems. We seem to be having a good handle on the technologies, but there's a great absence of the workings of the larger world. In fact, these two illustrations are really kind of metaphors. The building on the left is a Leeds Platinum. It has a green roof, and it's about as good as it can get. And it's certainly green. But it does not borrow anything from nature's legacy. The building on the right attempts, at least in an architectural way, to integrate in a biophilic world with the larger world. So I'm going to give you a few examples of eco-machines, starting with some of the very earliest experiments that are now old, for waste treatment, nutrient recovery, and food production. You're looking at a pond which is filled with toxic wastes. Of the top 15 EPA priority pollutants, they're all in that pond, plus heavy metals. That pond, by the way, is above the drinking water table of that town, and that's coarse sand. It's not lined. This is a little bucolic New England town. Actually, it's on Cape Cod. So the question then was, how can we use nature's operating instructions at about 1/10, maybe even 1/100th the cost of high-tech technologies to eliminate those hazardous materials? The first thing we did was to say sunshine is at the very epicenter of life. It drives all of the great systems that sustain us. Why don't we optimize lighting? And hence the clear-sided tanks. This is right in the middle of a landfill where this facility was done. The next thing we did, and this is the part of the story that I would like to convey, we went to over a dozen wild environments, from salt marshes to pig wallows, wet places in the woods, ponds, and we brought literally tens of thousands of species out of the wild and put them in those tanks. Then what we did was start to introduce the waste into those 21 tanks. There is another element, which you'll see in a moment. Each tank had a different strength and concentration of waste, and each tank through self-design, self-organization, which is natural to ecological processes, produced its own unique ecosystem related to the strength and the concentration of the waste at that point. When the great biologist, the late Lynn Margulis, and her students analyzed the communities on the walls of those tanks, they had never on the face of the earth seen those communities before. They were brand new, but they knew every one of the organisms. They were in a different context. And there were literally thousands of species that finally stayed and did the work. And after 10 days, the priority pollutants were removed, all but one, which was 99.99% removed. The heavy metals were sequestered. That's another story, but very, very effectively. So that water is meeting drinking water standards. And that was one of the first experiments that led to the development of eco-machines that are now in 10 countries, and there are over 100 projects around the world right now. Moving further north to Vermont, you're looking at a sewage treatment plant treating about 100,000 gallons a day of waste to very high standards in order to discharge it into the very vulnerable Lake Champlain. And one of the systems that developed here was for sludge management, and this represents a 100,000. It took 100,000 koi and carp, this is mostly koi, to manage the solids within the system towards the far end. The value of the crop in that tank is about $100,000 for the wholesale, and retail it's probably 10 times that. So that what we're doing is now starting to insert economic elements into these complex ecologies. And it's just a drawing to show you the same cellular design that you saw earlier is characteristic because, as I say, the self-organization and self-design varies at each stage in the process, and unique sets of organisms adapted. This is the Omega Center for Sustainable Living in Rhinebeck, New York. It is the first building to be certified as a successful Living Building Challenge building. It also is a LEED Platinum building. And its function is to provide all of the sewage management and the recycling for a campus that generates 50,000 gallons a day. It is also a classroom. And you can see looking in that there is a fair amount of light coming in from the southern side. Surrounding the building is a very wonderful constructed wetland, which provides the primary waste treatment and eliminates most of the need for odor control within the building itself, although we can control odor in buildings when we have to and do. This is a view of the aquatic phase, if you will, the open water phase of the waste treatment process. The water here is sterilized and recycled and reused on site. It's very people-friendly. Classes are coming there all the time, and including yoga classes early in the morning. And it has recently demonstrated, and as far as we know, the first living technology to do so, eliminate the great majority of endocrine disruptors, or sometimes called gender benders, these chemicals that appear in the water. So here again, we're showing a unprecedented level of purification, and we're now learning, and this is the key, that if we don't put all of the 6 kingdoms of life, the archaebacteria, the eubacteria, the proctista, the fungi, the animals, and the plants, if they're not all in the system, they don't have this marvelous meta-intelligence that I'm talking to you about that we need to tap into. I've been dreaming about designing a eco-industrial park for a long time. Sort of got partway there with this project. This is in the center of the city of Burlington, Vermont. It's called the Intervale. There's a power station in the background, and it is basically a incubator for future Vermont farmers. There are 900 acres down there, and they work together. There's a lot of research on crops. Here you're seeing wine crops and strawberry crops being evaluated. Hundreds of species. Cook's Garden used this site to evaluate food crops. And it is a very active place with, I think, probably at any given times about 30 to 40 farms. And what my group did was to go down there and do an inventory of what was going on, what were the wastes, what kind of businesses could be developed down there and integrated into this one synergistic system, which would allow farmers that to not have to go to a large scale to have a livelihood. And one of the things that we also did, working with graduate students from the Dutch Business University, Nijrode, was to calculate what businesses might or might not work based on the agriculture in the valley. So we came up with the ideas of a bakery and a brewery, a food processing, a restaurant, and so on that had to be part of the eco park itself, and if it was going to drive. And because I was using students, the most important part of the project was the brewery. That gets students really excited and enthusiastic. And one of the things that we found as we began to develop this, and a number of companies grew out of this, was that the managing of materials was one of the keys in the whole design process, the center of that drawing. And that bringing together materials and producing various food webs from them was the key to the economics. On the right in this drawing, you can see some of the crop production schematic that we planned. Then we began to do some pilot scale studies. And one was the sort of aquaponics, because in an earlier incarnation, I started to develop aquaponic systems in the early 1970s at the New Alchemy Institute. One of the things that we found was that when you're designing an intensive system, you need to have a wild ecology from which to design your relationships. And so I chose for this project an ecology that I had known for a long time because I had been an oceanographer, and that was the eelgrass communities of the coast. And just figured out all the things they do, how they do it, how they solve the problems, how they clean up coastal water, how they support bay scallops. And we simulated that system in a freshwater setting to grow fish and greens and vegetables. And I don't have the time here today to explain this system to you, but what it did was borrow the intelligence of the eelgrass community and interpret it. We had analogs. And by the way, the man who really pioneered this was Walter Adey at the Smithsonian Institute in Washington, when he began to simulate wild ecosystems in greenhouses. He had to learn not only how to provide life support for them, the kind of things that you people at NASA and at the German Space Agency are doing, but also how to assemble them. In other words, you don't just dump all the animals into a system like that at a time. You build them up in a successional way, the way ecology operates. And anyway, these are some photographs of the pilot. And what was really interesting, and this is published in the journal Ecological Engineering in an article called Ecology Applied, we were able to purify the water, close the cycle, and provide with systems that we were working with all of the feeds for the fish. And so the very purification processes themselves, because it's an eelgrass type design, are producing feeds for the fish in the same cycle that's purifying the water. The waste we worked with was the primary input was brewery waste. The liquid went into the aquatic system, and the solid part of the waste went elsewhere. And here, a common activity, we inoculated oat straw and the brewery waste with the mushroom spawn, and produced crop after crop of mushroom, which then converted the brewery waste into a very high quality product, including an animal feed, by the way, which we then in turn used to drive converted using the earthworms into a very high quality soil. Because I think in an urban environment, we're going to have to build a lot of soil from scratch, and it's something that we can do and will do. And it means that we don't have to work with contaminated soils. We may have to do something with those soils, and we will, but we don't have to work directly with them. And I know a number of you here are doing this sort of thing. And from that, during the wintertime, we did not want to offend any of the farmers, seasonal farmers. So during the wintertime, we provided crops beginning in early November right through to the beginning of May in the greenhouse with some supplemental lighting, but not a lot. This is an artist's rendition of the agro-eco-industrial park. It didn't get built for a very complicated series of reasons, including Native American burial site is right there. But more recently, my organization has begun work on the conversion of a large coal-powered station into an industrial park, and hopefully before too long we'll be able to tell that story. So getting back to the theme of how can we push the technologies as the intensification process goes on, but at the same time link what we are doing to the teachings of nature, to the legacy of evolution. And sort of ending here with a slide of a skyscraper by one of my graduate students, which is basically inspired by a termite mound, the study of termite mounds, and using them ecomimetically to try and create the integrated structures of the future. And so maybe what we're doing here is not only urban agriculture, but integrating functions within the urban environment, where civic functions, education, living, and food production are all part of a woven fabric of life within the urban environment. If we go that direction, I think we might even get higher support than if we simply go forward as an agricultural activity, as important as that is. Thank you very much.
Thank you, John. A very inspirational talk. We have time for a few questions while our next speaker gets ready.
Okay.
Yes?
Yeah. Well, I can talk loud. Can everybody hear me? Yeah. Oh, the web. Yeah, that's right. Well, as far, I guess two things. One, the tilapia that you're growing, since you have this full range, one of the downsides of farm-raised fish is that they're fatter and they don't have as many omega-3s than wild fish. Is your stuff tilapia equivalent?
No, I think that's a valid criticism. For example, tilapia is not an oily fish, and it doesn't go around with a lot of omega-3s. Now there are There are supplements to diets that can enhance the levels, but I wouldn't use tilapia to go for my omega-3. I would get some herring in the fall, or even go fishing for salmon.
I guess I'm going back to the diet of the fish, where instead of
Yeah.
feeding them
Oh.
fish meal or cornmeal, soybean or whatever, if you fed them
Basically what they're feeding is on plankton, the animal plankton. They're feeding on the attached algae. There are screens that are grown in one tank and put in the tank for the fish to feed on. They do all their own feeding off the screens, they're called algal turf communities. There are about a dozen species in fresh water, and they all live together in this cozy little Lilliputian forest world. And that's the diet, because they also attract animals. And then we supplement it with earthworms ground up with the floating aquatic plants, the azolla and the lemna, the duckweeds. And that's the mash that we supplement their diet with.
Thank you, John.